Alright, so in this example, we're going to be using superposition to find Vx. So Vx is labeled up here. It's actually labeling this node that I've already pre-drawn, which is more conveniently labeled across this resistor. Notice that this resistor is in parallel with this current source and this dependent current source as well. Superposition in this case will be Vx, what I'm trying to find, equal to Vx prime plus Vx double prime. So there's only two pieces because I have two independent sources. This is a dependent source. It won't show up in here. If I had a third independent source, say another current source or another voltage source, then I would have a third. I would have a Vx triple prime. And again, if you want to use Vx1 and Vx2, go for it. It's fine. So what we want to do when we're solving one of these problems is we want to pick an independent source. So I'm going to start with the 25 volts, and we want to redraw it with every other independent source turned off. So notice I'm saying independent source. We're going to leave the dependent sources on because what they do depends on the independent sources. So they don't do anything by themselves. If I turned off both of these things and this was the only thing on the circuit, you'd find that it doesn't do anything. All this is going to do is modify currents and voltages. So we've redrawn the circuit here. So we have our 25 volts. We have our 20 ohms. This current source is going to go away. I'm going to turn it off. It's going to be 0 amps, which is an open circuit. I have this 4 ohm resistor in this 0.1 Vx. So this is our dependent source. So we leave that in. I've labeled node 1 and node 2. I also have a node down here. You can call that node 3, node 0, whatever. So because they labeled it as ground, I generally call our ground nodes 0. Our resistors are not in series, so we can't do a voltage divider. They are also not in parallel, so I can't do a current divider. So what I'm left with is we go back to KVL and KCL, and we try to find the most convenient places to do those so we can isolate our variables. So we're going to end up with multiple equations that we're going to combine in together. We also have Ohm's law. So in this case, I have Vx here and I have Vx here. So note that I call this Vx prime and this Vx prime. They're not the original Vx. They're only the part of the Vx caused by the 25 volt source. So this one's already labeled as going up into this node 2. If I follow passive sign convention, then this current will come out. And if I follow passive sign convention, then this is an active element, so we'll go from negative to positive. This is in series. It'll enter this node 2. So I know the directions for everything entering and leaving node 2. So let's go ahead and start with that, mostly because I have Vx at 2 spots on that, and I really want to know Vx. Oh, sorry, Vx prime. So In equals I out is our KCL at 2. So that's going to be our 0.1 Vx prime is entering. Also, I have this current, which I'm going to just call the current through the 20 ohm resistor. We will replace that later using Ohm's law. And then I also have the current through the 4 ohm resistor, so I've labeled that here, so following passive sign convention. So I could do a KCL at 1, but that's not going to tell me anything because I will never know, at least not until the very end, I won't know the current through a voltage source. So that's not going to be useful, so that means we want to go look for KVLs. So I could do a KVL over here, but it's kind of a similar problem. I will never know the voltage across the current source, dependent or independent. So that's kind of out of the picture. So what I'm left with is I need to do a KVL around this loop. So I do a KVL, and I called this 1 in my example. So we'll get rid of that. We'll call this loop 1. Sorry about the drawing. I know it's a little messy. So we'll go KVL around 1. So I'll start down here. So we're going to have, so this is the sum of the voltages around the loop equal to 0. So we're going to start, so minus 25. And again, if you want to grab the sign as you leave, go for it. I just always grab the sign as I enter. And then because I'm following passive sign convention with this, I'm going to put my polarities on here. So this is going to go from positive to negative because my current's going this way. So then we're going to get plus the voltage through the 20 ohm resistor across the 20 ohm resistor, and then we're going to come here, and this is already labeled for us, so this is going to be plus Vx prime, and then I'll come back to where I started. So that'll all be equal to 0. And so what I want to do is I want to get rid of the I20 ohm, the I4 ohm, and the V20 ohm. And I can do that with some different methods. Because I want to keep everything in terms of Vx prime. That's what I want to do with everything. So let's start off with the 4 ohm resistor, because that's going to be the easiest one to do a substitution with. So I have Ohm's law, and I know that Vx prime is equal to this I4 ohm times that 4 ohms. And I don't need to put the ohms here because it's already a resistor. So this is just V equals IR at this resistor. I'm going to solve it for the I4 ohm. So I4 ohm is Vx prime over 4. And now I can sub that in here. All right. So the next thing is I20 ohm and V20 ohm. These are both of this 20 ohm resistor. I can do another Ohm's law and basically relate these two so that I only have one variable. So we have another Ohm's law. So we know that V of 20 ohms is equal to I of 20 ohms times the 20 ohms itself. So we have a choice. We can either sub in for the I20 or for the V20. It doesn't really matter in this case. It's already solved in terms of this. All we want to do is just get a common variable. So let's drag our two equations down. So this one will come down here. We'll have 0.1 Vx prime plus I of 20 ohms is equal to Vx prime over 4. This one, when I bring it down, will become negative 25 plus 20 times I of 20 ohms plus Vx prime, all equal to 0. I'm going to solve one of these for I20 ohms and sub it in so that the only variable left is Vx prime. It's just your standard algebra. Basically, all we're doing here is algebra. You've already done the circuit part. So once you go through your algebra, so we will plug in our V of 20 ohms, our I of 4 ohms. We'll get our equations here. We'll solve them both for I20, and then we'll say that this left-hand side equals this right-hand side. I'll multiply by 20 to get rid of our denominators, and you'll be left with a negative 2 plus 5 equals 25 minus 1 Vx prime. You'll do your algebra, and you'll find that Vx is 25 over 4. Sorry, Vx prime is 25 over 4. And at this point, you are halfway done. And we now get to do this again, but for the current source. So we're going to do all this again. We're going to redraw our circuit. So I have 0 volts here. And we have our 20 ohms. And then this time we're keeping the 5 amps on. We still have our 4 ohm plus or minus Vx. This time it's going to be Vx double prime or Vx2 if you want to call it that. And then I have my current source, 0.1 Vx. So if you really wanted to, you could slide this 20 ohm resistor over here. Everything's in parallel, which is actually kind of nice. That means that I have a common node up here, node 1, and then a common node down here, node 0, or the ground node. So I can do a KCL at that node 1. So this will be going up. This is a resistor. We already have polarity, so it will be going down. We know that this will be going in. With this one, I could say either direction, but knowing that it shares this voltage, so this voltage is across all of these elements, then I know that its polarity will be this way, where this is the the positive, and this is the negative, which means I expect the current to go this way by following passive sign convention. These labels are somewhat arbitrary. You get to pick the first one, so I can pick polarity or current direction. The second one has to follow passive sign direction. In equals I out. And so going in, I will have, so this goes out, I'll have the 5 amps going in. This leaves, I will have the 0.1 Vx double prime. Let me relabel that as Vx double prime. Going out will be the current through each of these. So I could call this I of 4 ohms. I'll do it real quick. So current through the 4 ohm and the current through the 20 ohm. I'm going to sub both of these out, knowing that I is going to be V over R. In our case, it's going to be Vx double prime over R for both of them, because Vx double prime is the voltage across both of them. So 5 is equal to 0.1 Vx double prime. For the 4 ohm, it is going to be Vx double prime divided by that 4 ohms. For this one, it's going to be Vx double prime divided by that 20 ohms. In this case, you have done all of the circuits and you're just doing algebra. Vx double prime is equal to 100 over 4, or 25. So if I compare these, Vx prime, which was the Vx caused by the voltage source, the 25 volts that I removed, is 4 times smaller than the voltage the voltage caused by the 5 amps. And really what I want to know is, what is the overall voltage? I think that's what the question asks us, but the more interesting thing is how much is each thing contributing? That's primarily why you would do superposition. So in that case, Vx is equal to Vx prime plus Vx double prime. So Vx prime is equal to 25 over 4. This is just 25. When you put those together, you will get 125 over 4, which simplifies down to roughly 31.3 volts. And again, if you had a third independent source, so say you added a current source out here or something, you would have a Vx triple prime that you would need to include in this. And you would have to do all this process again one more time for that third source.